Okay, in our final flipped lesson for this topic and really for the year, we're going to look at electrochemistry. And in a sense, what we're going to look at in this video is how we use the concepts of oxidation and reduction that we learned about in the first video and the metal reactivity series that we learned about in the second flipped lesson, and how these are applied to make batteries and to understand how batteries work. Let's get into it. So, as usual, we've got all the things that we need to know, if you like, in blue here, and all the things we need to be able to do, our success criteria here in green. Just a couple of terms I want to introduce you to before we start. The first is galvanic cell, which does come up here. A galvanic cell is essentially a battery. They convert chemical energy to electrical energy, and they do this from a spontaneous redox reaction. So a reaction that just wants to happen because, for example, it's favoured by the metal reactivity series. Now, if you like, the opposite of a galvanic cell is an electrolytic cell. They use electrical energy to drive a non-spontaneous redox reaction. So in terms of batteries, when we are charging a battery, we are using electrical energy to drive a non-spontaneous reaction, and then that spontaneous reaction can occur during discharge to produce power. So a rechargeable battery, when it's charging, is acting as an electrolytic cell. When it's discharging, is acting as a galvanic cell. Next year, we'll do a lot more on electrolytic cells and how they're used for metal production and lots of other interesting things. But for now, the main reason we introduce that term is that's what's happening when a battery is charging. So this here, and we'll have a go at building this in the lab. This here represents a simple galvanic cell made out of zinc and copper, which were the two metals I used in the last video. And we saw that zinc is more reactive than copper. Now, when we do it all in the same container, basically the zinc loses electrons and the copper gains electrons to form copper metal. Here, we are, if you like, separating out the two half reactions, the two half equations, into what we call two half cells. And these are connected by basically a wire. Here we'd put a voltmeter so we can see the flow of electricity and how much energy it's got. But this could be a light bulb or a laptop or a mobile phone or anything that's being run by this battery. And basically, because electricity is a flow of electrons, so if we separate this anode where electrons are being lost, where oxidation is occurring, from the cathode where reduction is occurring and electrons are being gained, and those electrons have to flow through a wire to get from one place to another, we can use that flow of electrons to produce electrical energy. Now, the charge has to make a complete loop through the circuit, so we need something here called a salt bridge. I'm not going to talk too much about the detail of a salt bridge in this video. It's just a way to allow charge to pass through. When we do the prac, you'll see how they work a little bit better, but you don't need to know too much detail on salt bridges other than we need them so that we can have a complete flow of charge. So, what's happening here? Well, at the anode, the zinc is going to form zinc 2+ ions because the zinc is the more reactive metal, so that's the one that wants to be oxidized. So it loses electrons. So, here we have basically the zinc is this is the zinc, loses electrons. Therefore, that is oxidation. Therefore, that is the anode in our cell. And over at this other electrode, the copper electrode, what happens here is that we have the gain of electrons, which is reduction, which makes it the cathode. So we can see here the copper ions gain electrons to form copper metal. And when we do this in the lab, and if we leave this running long enough, you'll see just a little fresh coating of copper starting to form on the piece of copper that's already there. So these electrons that are lost basically will then flow through that connection from one electrode to the other, setting up our flow of charge. Now, the charge needs to balance, so what we do here is have a salt bridge. We don't want the copper sulfate to be able to mix with where the zinc is, otherwise then we'll just get copper coating onto the zinc. So we use a salt bridge, and that lets ions flow through, so charge can flow through, but it won't let the copper ions or the zinc ions, well, the copper ions are the main problem, because if the copper ions could mix here, then the copper would just form on the surface of the zinc, rather than separating out these half cells and allowing this battery to operate and us to be able to produce useful electrical energy from it through, capturing that flow of electrons. So, what have we done there? We've identified the cathode and the anode. We've identified the direction the electrons flow. We have got a diagram of a galvanic cell. We've written half equations, they're down the bottom here. And we've compared the operation of different types of batteries in terms of galvanic and electrolytic, in terms of rechargeable and batteries needing to do both, and non-rechargeable batteries just being galvanic cells. So that's the most important part with the galvanic cells and the batteries, but I am going to, in the next slide, talk about another really important type of battery, and that's a rechargeable battery that we use a lot, which is the lead-acid battery. Again, we will demonstrate this in the lab, but just so you've got that background of how the lead-acid battery works, I'm going to go through that in the next slide. So, a rechargeable galvanic cell. In rechargeable galvanic cells, rechargeable batteries, the discharge reaction while behaving as a galvanic cell, must be able to be easily reversed by application of a potential difference during charging, when it's acting as an electrolytic cell and converting electrical energy to chemical potential. So, probably the two most common rechargeable batteries are the lead-acid battery, which has been around for a very long time, and then obviously the lithium-ion battery. Now, the lithium-ion battery chemistry is a little bit more complex, so we're not going to go into that within this course, but we are going to talk about the lead-acid battery. So what happens at the lead-acid battery is that you start off with two electrodes, and both those electrodes are made of you start out by using two electrodes that both are made of initially bits of lead. And then you have an electrolyte that is made of sulfuric acid solution. So that's sulfuric acid. That has two purposes, if you like. The first purpose of that is that it acts as an electrolyte. So an electrolyte is a solution that can conduct electricity. Sulfuric acid. So it acts as an electrolyte. So how does it act as an electrolyte? Well, it's a strong acid, so when you put it into water, it completely ionizes and it releases hydrogen ions and sulfate ions. Basically, I'll just show here, try and get into using our subscripts. So that allows charge to move through. The other thing, though, that the sulfate does is that it reacts with the electrode, it reacts with the lead surface to form lead sulfate. So we might start with the charging process down here first. So basically the lead reacts with the sulfate and we get on the coating of both electrodes, to start with, we get a coating of lead sulfate. From that reaction of the lead with the sulfuric acid. We're not going to go into the details of how and why that happens. So, when we charge that battery up, let's go back a step. One thing that's really important about lead is, we talked about this in the first concepts, is oxidation number. We can get lead metal and the oxidation number of lead metal is 0 because it's the pure metal. We can get our lead sulfate. Now lead sulfate, the oxidation number is +2 because the sulfate has a 2 minus, the lead has a +2. But lead also has another oxidation state, which is the +4 oxidation state, when it forms lead oxide, when it reacts with oxide ions. So this battery is going to make use of all three of those oxidation states. So let's go to the negative terminal, if you like. So what happens at the negative terminal is when we charge this, we're basically pushing electrons into the circuit. So we get the gain of electrons. So gain of electrons is reduction. So therefore it's the cathode. So what happens is that lead sulfate, which is the lead with the +2 oxidation state, gains electrons and forms lead metal, and we get sulfate ions as well. So when we build this battery, and we'll do this in the lab, we'll see a nice fresh coating of lead go onto this electrode. At the other electrode, electrons are being lost, so therefore that is oxidation, therefore that is the anode. Then what happens there is the lead sulfate, which is basically the lead 2+ ions, are forming lead oxide, which is the +4 oxidation state. So that's our redox couple. So we balance out, the balancing here probably is a bit trickier than you would have to do, but basically we balance out with water and hydrogen and electrons and all that sort of thing, and we get this reaction here. Now that lead oxide is a brown solid, and on this positive electrode during charging, you'll see this brown coating form on the electrode. Then when we discharge this, we see the opposite process happening. So at the negative terminal, we get the loss of electrons, which is the oxidation, therefore it's the anode. So this fresh lead loses its electrons to go back to form the lead sulfate, which is the lead with just the 2+ charge. Basically, these equations here in yellow are the ionic equations, because the sulfate is effectively, it's not quite a spectator ion, I'm sort of fudging it a bit, but to me, just focus on what's happening in the yellow, don't worry too much about what's happening with the sulfate. So the lead is losing its electrons, so the electrons can flow from this electrode to the other electrode. On this electrode here, the lead oxide, which is the one with the +4 oxidation state, so it's a bit like the +4 charge, is going to gain electrons and form the lead 2+ ions. So here we have oxidation state going from 0 to +2 oxidation, increase in oxidation number. Here it's going from +4 back to +2. So all the electrons here that are lost, they go to this electrode, they're gained at this electrode, and that is what basically allows our charge to flow from the negative terminal to the positive terminal, for us to capture that electrical energy. As I said, I don't expect you to remember the detail of the lead acid battery, just the big picture, and we will do this as a demo in class, so you get a bit better, clearer understanding of what this looks like. So yeah, that is the theory that we need to know about batteries. In the practical task, we are going to, you are going to build a battery, either one based like on the copper zinc battery, or like one based on the lead acid battery. And then you're going to design an investigation to look at one factor that affects how well that battery operates. So it might be if you change the charging time on a rechargeable battery, how does that affect the discharge time? It might be if you change the size of the electrodes, how does that affect how much current or voltage that the battery delivers? It might be if you change the thickness of the salt bridge between the two, how does that affect the performance of the battery? So there's lots and lots of different things that you can think about that could affect how effectively a battery operates. And what you're going to do is consider what all of those are and then design an experiment where you're going to build a battery and test out how that works. And we're going to do all that in the lab, and your report on that will be your assessment and your final assessment task for the year and your assessment task for this topic. Okay, thank you.